Up until this point, we've only looked at derivatives of functions of the form y equals x. In other words, we could say that y is defined explicitly in terms of x. It's only defined in terms of x. So we've dealt with functions like f of x equals x squared plus 1, y equals sine of x, things like this, where y is solely a function of x. It only depends on x. But relations between variables can also be defined implicitly, so we can use more than one variable. For example, when we look at the unit circle is defined by the equation x squared plus y squared equals 1. If you were to graph this relation, what you would see is a circle centered at 0, 0 that has radius 1. So I'll see if I can draw it. That's not bad. You would see a circle that's centered at 0, 0, and then the radius right here is simply 1. But if you look at this looks a little bit odd because this is not a function. If you were to use the vertical line test, it would fail, right? Here it intersects right here, and I know if I have a vertical line that intersects more than one time, it's not a function. So these implicit relations may not be functions, which is a little bit odd for us to be working with, but we can still use a lot of the same ideas that we've used in calculus here. We can use a lot of the same derivative ideas here for these types of relations. If I were to take something like this, just to drive this point home, just to drive home the point that this is not a function. If we were to solve for y, we would end up with two functions of x. So we would end up with a positive and a negative. And we're actually going to show this here. So I'm going to work with this same equation, the same relation, x squared plus y squared equals 1. We're going to take the derivative like we normally would, and then we're going to use implicit differentiation, sort of a new idea for us, and find the derivative that way, and show that we actually get the same thing. There's pros and cons to kind of each side, but we'll see kind of which side is easier for us in this case. So if I'm working with x squared plus y squared equals 1, if I wanted to find y prime, most of us would have to go and, before we have implicit differentiation, we would have to solve this equation for y and then find y prime. So it's really a two-step process. So alright, if I'm working with x squared plus y squared equals to 1, if I solve this for y, I'd have y squared equals 1 minus x squared. But when I solve this equation, here's where I'm sort of going to run into trouble. I end up with y equals plus or minus square root of 1 minus x squared. Here's really the two functions of x that I mentioned earlier. So what I really have are these two different functions. I've got y equals square root of 1 minus x squared, and y equals negative square root 1 minus x squared. These are two separate functions, so they'll have two separate derivatives. Now there's a few things that we can do to kind of speed up that process and use some tricks to make that process go a little bit smoother, but at the end of the day we still have these two functions. I'm going to call these y1 and y2. So y1 will be the positive square root, y2 will be the negative square root. So let's find the derivative of y1. Let's do that in red right here. So if I want the derivative of y1, I'm just going to rewrite my function up here. y1 is equal to square root of 1 minus x squared. I know I'm going to, I need to take the derivative, which means I probably should rewrite that square root. So this is really 1 minus x squared raised to the 1/2 power. So this is still y1. I haven't yet taken the derivative. I notice these parentheses and I say, boy, this looks an awful lot like the chain rule. So my inside part, this would be my u. U would be 1 minus x squared. So if I were to take the derivative, let's see if we can do that a little bit quicker this time. y1 prime going to multiply by my power, so 1/2 times, inside part stays the same, 1 minus x squared, subtract 1 for my power now, raised to the negative 1/2 power, times the derivative of the inside part. Well, the derivative of 1 minus x squared, that is negative 2x. And then I would take this and simplify it a little bit. So let's see, 1/2, that can cancel the 2 there. So y1 prime is equal to, let's see, all I have is, let's see, I got a negative x. So negative x in my numerator, negative x divided by 1 minus x squared raised to the 1/2 power. There is my first derivative for y1. Now, if I wanted to go and find the derivative for y2, there's a few, I could go and kind of repeat this whole process. It would be a very, very similar derivative. I would say, well, y2 equals negative square root 1 minus x squared, and then I'd rewrite it, and then I'd use the chain rule, and it'd be a very similar process to what we just saw. Or I can say, well, what's the difference between y1 and y2? The only difference between these two is this minus sign, which really that minus sign is just a constant multiple of negative 1. Remember that constant multiples don't really impact your derivative. If you have a constant multiple in your original function, that constant multiple, you just bring that to the derivative. You just multiply the derivative by that. So that means that if I wanted to find y2 prime, the derivative is going to look almost exactly the same as y1. So it's going to look almost exactly the same as this. I'm just going to have a constant multiple of negative 1. So my y2 prime, it's going to look almost the same as negative x all over 1 minus x squared raised to the 1/2 power. I'm just going to go ahead and multiply that by a negative 1. So you could say negative 1 like that. We could also just say, put the negative sign right there. And then, yeah, we would probably want to simplify that just so that it's easier to work with. Then I have x over 1 minus x squared raised to the 1/2 power. So here is my y2 prime. So, okay, it wasn't easy. It was still pretty tricky, right? Because we ended up with these two functions. We had to use the chain rule. It was a pretty difficult problem, I would say. I want to do a little bit more with it, though. So suppose I wanted to find the slope of the unit circle at 1/2 comma square root 3 over 2 and 1/2 comma negative square root of 3 over 2. Okay, slope of the unit circle makes me think about slope of the tangent line, right? So we're thinking about the derivative when we talk about slope, right? We're thinking about f prime of x or y prime. But here is the problem that I now face. I have these 2 points, which, okay, that's great. But I had essentially 2 derivatives, right? I ended up with 2 derivatives depending on whether I was looking at the positive or the negative case. I said y1 prime was negative x divided by 1 minus x squared to the 1/2 power, and y2 prime is positive x over 1 minus x squared raised to the 1/2 power. How do I know which one of these to use? Do I take this point and plug it in here, or do I plug it in here? I don't know. So what I need to do then is I need to look at how I came up with those derivatives. Raised to the 1/2. I need to look at where did these derivatives come from? How did I come up with these? Well, remember that we found those by saying, okay, we have positive square root 1 minus x squared, we have negative square root 1 minus x squared. In this case, I think it would be really helpful if we kind of visualized what do each of those look like. So I'm going to graph the unit circle here. Let me do it right here. Actually here, So we said the unit circle, it's a circle centered at 1. It looks something like this. But really what I have is I have 2 separate functions. I'm going to have this top function, here's the positive case. That's the red one right there. So this is really y1 equals square root of 1 minus x squared. And then the bottom half of the unit circle, that's my y2, that's my negative square root 1 minus x squared. So this at least gives me some information about, okay, what do these curves actually look like, because then I can sort of match the derivative with the correct curve. All right, it feels like we're maybe getting somewhere here. What I'm going to do is I'm going to look at each one of these points. So let's start with 1/2 comma radical 3 over 2. I'm going to think about where that point lives on the unit circle. And I don't need to be too precise, but I notice that this is a positive number, this is a positive number, must be in the first quadrant. Let's say probably right here-ish, give or take. So if I wanted to sketch in the tangent line, I would see something like this. So when I'm working with this function, or excuse me, this point, 1/2 comma radical 3 over 2, I know I'm talking about a point that's on the curve of y1, so it probably makes the most sense for me to use the derivative of y1. So next I've got to take this point and I've got to plug it in. So let's do that. How about we do that in red? So we will do that. I don't want to get too lost here. Here, actually, let's do this. All right. So when I'm working with y1 prime, I'm going to take 1/2 comma square root of 3 over 2 and plug that in. And really, this is just a function of x. I really only need the x value. I don't know why they're giving me the y value here. So 1/2, let's see, negative 1/2 divided by 1 minus 1/2 squared to the 1/2 power. This is negative 1/2 over 1 minus 1/4 to the 1/2 power. This is negative 1/2 over 1 minus, what do we have here? Oops, not 1 minus 1/4. We can simplify that. Let's go ahead and erase. That will be 3/4 to the 1/2 power, which that's really negative 1/2 times, let's see, if I, let's see, I'm going to multiply by the reciprocal here, 4 over 3 to the 1/2 power, which that's really negative 1/2 times, if I take 4 to the 1/2 power, that's really just the square root of 4, so that's going to be 2 over 3 to the 1/2 power, that's square root of 3. These two cancel. I'm left with negative 1 over radical 3. If I wanted to simplify that, negative square root 3 over 3. So there's my slope. Holy moly. That was a complex function we were dealing with. But hopefully we can see, okay, the slope of this black line that I drew in earlier, that's negative, and we ended up with a negative slope. So at least we kind of have some way to say, yeah, that seems like a reasonable answer here. If I wanted to know now the slope of the line at 1/2 comma negative square root of 3 over 2, so where is that point? Well, this point, my x value is positive. I'm on the right half of my y-axis. Negative square root of 3 over 2, that's below the x-axis. It's in the fourth quadrant. You're talking about this point right here. So, okay, what does this look like? And at this point, we can sort of cheat a little bit. Let's see here. This is, so because it's on the bottom half of my unit circle, right? Because this point is on the bottom half of my unit circle, I'm looking at y2, which means I probably want to plug in 1/2 to the derivative of y2. So I want y2 prime of 1/2 equals, so here I've got positive 1/2 divided by 1 minus 1/2 squared raised to the 1/2 power. And I'm just going to kind of take a peek at what I had above. This is exactly the same thing as this, I just don't have the negative sign. So yeah, I could go do all that work, and I probably should just to be safe, but I know if the only difference is this negative sign right here, I'm going to end up with square root 3 over 3, but I'm going to end up with a positive square root of 3 over 3. So there's the slope. Oh my goodness. So that's one way you can do your problem, and that's kind of the only way that we know how to do this problem, is using explicit differentiation, because we're writing y as an explicit function of x, and then we're taking the derivative using our derivative rules. In this case, we use the chain rule. I'm going to show you a different way to do this, though. So now I'm going to take that same function, so the function we're working with, x squared plus y squared equals 1. It's a little bit hard to see. Let me see if I can erase. I want to find dy dx, or y prime. It doesn't really matter which notation you use. I'm going to find that implicitly from the equation of the unit circle x squared plus y squared equals 1. So when I work with something implicitly, let's actually talk about the difference between explicit and implicit differentiation real quick. When I take the derivative explicitly, when I use explicit differentiation, there's really two steps. If you look back at what we did, it said solve this equation for y, then find y prime. So we solved for y. Solve for y is the first thing that you do. Second thing is that we took the derivative. Take derivative. What implicit differentiation does, if I'm working with implicit differentiation, it essentially takes the order of those two things and flips them around. Instead, I'm going to take the derivative first. And this sounds kind of silly, but in this case, it'll be really nice. Take the derivative, and I'm going to add in one reminder. The chain rule is going to be really important. That's why we talked about the chain rule right before this section. It's going to be really, really important here. And then the second part, we're not going to solve for y, because we're not really interested in y. We're going to solve for either y prime or dy dx, just depending on which notation that you're using. I think I'm going to use dy dx. I prefer to use dy dx in this section in particular, just because it's easy to mix up y and y prime. So okay, I'm gonna try using this implicit differentiation over here. Let's see if it's any easier. So I'm working with this relation x squared plus y squared equals 1. The first step says take the derivative. Well, okay, I'm going to take the derivative. If you come across a term that is written only in terms of x, you're going to take the derivative of that term exactly like you normally would. So derivative of x squared, that is 2x. Okay, that's easy enough. When I take the derivative of a term that has a y, though, here's where we're going to be using the chain rule. This is where the chain rule is going to be coming into play. Because I want to think about y, this y is a function of x. Or multiple functions of x, as it is in this case. So y is a function of x. So what I really have here, when I say y squared, is I have a function y squared inside of another function, inside of the squaring function. So I have a function inside of a function, which means, yeah, we're going to need the chain rule here. So when I use the chain rule essentially says, all right, we're going to take the derivative of this outside part. We're going to take the derivative of y squared. So when you think about it, it's kind of the same as the derivative of x squared. We're just going to have 2y, but that y is a function of x. Remember, whenever we had the chain rule in the last section, we always multiplied by u prime at the end. We always had to multiply by the derivative of that that inside function. So I'm going to say 2y to the first times, actually I don't want to say 2y to the first, 2y to the first, yes, but I don't want to say 1 right there because I don't want us to get mixed up and think that's a y prime. I'm going to multiply by the derivative here. So I'm going to multiply by dy dx. You can use y prime here if you'd like, but I think that having y and y prime can be a little bit confusing. And that's the derivative of this term. It looks like 2y times dy dx. So really what you have here is you have, this is your f prime of u times your u prime. This is the chain rule coming into play. But at this point, we've used our chain rule. We just need to go over to the other side. And at this point, the hard stuff's done. Derivative of 1, that's just going to be 0, because it's a constant. Well, cool. I only have one derivative. This is nice. Before I had like y1 and y2, and it just got really messy. Here I just have the one function, which is really, or I shouldn't say it's a function. I have this one relation. So now I'm just going to solve for dy dx. So okay, I'll subtract 2x. I've got 2y dy dx is equal to negative 2x. dy dx is equal to negative 2x over 2y. We can, of course, simplify that to be negative x over y. Well, hey, look at that. That's a whole lot simpler than saying, well, y1 prime is equal to negative x over 1 minus x squared to the 1/2, and y2 prime is x over 1 minus x squared to the 1/2. Here I just have this one little, it's just negative y over x, that's it. Working with this equation is actually a whole lot easier as well. So now I want to do the same exact thing. We just did this earlier for our other derivatives. Find the slope of the unit circle at these 2 points at 1/2 comma square root of 3 over 2 and 1/2 comma negative square root of 3 over 2. Here's another really big reason why implicit differentiation is so nice. Before I had to think about, okay, is this on y1 or y2? Is this point on y1 or y2? And I had to figure out which function I was kind of living on, right? Whether I'm on the top half or the bottom half, and then that told me what derivative to plug it into. Here, this isn't a function. This is actually just a relation. It's a relation between x and y. So it doesn't actually matter whether it's on the top half or the bottom half, because I have y in my equation. That's actually going to take care of that problem for me. So if I were to rewrite the derivative here just so that we have it in front of us, dy dx equals negative x over y, I'm just going to take 1/2 comma square root of 3 over 2. And ideally, if implicit differentiation gives us the same result as explicit differentiation, we should end up with the exact same solution we did before. So we should end up with negative square root of 3 over 3 and positive square root of 3 over 3. So let's test this out and see. Let's start with the results. I believe it was 1/2 comma square root of 3 over 2. We should end up with a negative square root of 3 over 3. And I'm actually going to write that over here. Negative radical 3 over 3. This is what we should end up with. So I'm going to plug this point into this function. And here's why. Remember I said earlier, I don't know why they're giving us the y value. Well, I actually knew. It's because this has both x and y. Look at my derivative. It has both x and y. It's really helpful that I have both the x coordinate and the y coordinate because I can plug both of those in. So let's see, negative x, that's negative 1/2 divided by y, that's radical 3 over 2. Let's see, I'm going to instead, let's do this. Let's multiply by 2 over radical 3, multiply by 2 over radical 3. My denominator, those are going to cancel, 2 cancels. Negative 1 over radical 3, which is negative radical 3 over 3. Look at that. It's exactly what I wanted. That's great. Because this was a whole lot easier than finding, solving for y and then plugging and then finding the derivative and having to use the chain rule. It was a nightmare. Well, let's just check one more time. Let's see if I get the same thing for this point right here. So let's see, dy dx, let's see, negative x, that's negative 1/2 divided by negative radical 3 over 2. So again, I'm going to pull the same trick I did before. And again, my denominator, those are going to cancel. 2's cancel. Here I have, oops, I forgot my negative sign up here. That would have been bad. Negative times a negative, that's going to make a positive. So I have 1 over radical 3, which is radical 3 over 3. Look at that. So this is the reason why we're going to take a little bit of time here in this section to talk about implicit differentiation, because it really helps us when looking at derivatives of certain relations. It helps us come up with derivatives that are not only easier to find, but also easier to work with. It also allows us to take derivatives of relations where perhaps that first step, right? Perhaps this first step of solving for y, maybe we can't even do that. What if we can't? I'd still like to be able to find the slope of the tangent line and do all the cool calculus stuff that we've been doing all this time. But what if I can't solve for y? If I can't solve for y, implicit differentiation is the only way that I can find the derivative. So this is going to be a really handy tool for this section. We're going to look at some more examples involving implicit differentiation, practicing it, and using it in context.